Okay, so I'm going to present, thank you, consolidating security notions in hardware masking, which I'm going to present next week at CHESS. In the world of embedded systems, we have a problem, and that's the fact that people can do side channel analysis. Luckily, we also have a solution, which is masking, or is one of the solutions. How do we know that masking provides security against side channel analysis? We know this because there are proofs. And to do proofs, we need a more abstract theoretical model of what our adversary can do. And a popular adversary model in our context is the probing model from Ishai, Shahai, and Wagner. And it says that basically the adversary can probe up to the intermediates in your computation. And these probes, they give you one exact and instantaneous value. And we also assume that different intermediates or different wires in your circuit, they leak independently from each other. So this is a very popular model because it has been proven that it also implies security in other more realistic models. So basically, we assume that if our circuit is secure in this model, then its implementation is also going to be secure against an adversary performing deed order DPA. So exploiting the deed order moments of the power traces or side channel traces. Now, what does that mean? What do we do when we're masking? Well, obviously we need to make sure that any D values in our computation does not give any information about the secret. So we're going to split our sensitive information into multiple parts, at least D plus 1. And how you do that split, there's many possibilities. For example, if the squares are exclusive OR operations, that you have Boolean masking. And when you're masking, you just need to make sure that you implement your functions in a way that they go from the split version of your variables, of your input, to a split version of your output, in a way that at no point during the calculation do you have D intermediate values that give any information about the secret. Now in hardware, this is a little bit more tricky than in software because we have glitches. A glitch is like a temporary change in a signal before it stabilizes at the value that you intended to compute. So during the glitch, you're actually computing a different function than what you're implementing. Let's call that the glitch function. And it's very difficult to predict what this glitch function is going to be because it doesn't only depend on your circuit, but it also depends on your platform, on your place and routing, on the execution environment, etc., etc. So if you want to try to model an adversary in the presence of glitches, we want to try to model this glitch function, it's very difficult. So we're going to work at a very high level. So this is our system. It consists of combinational logic and sequential logic. The sequential logic, they're memory elements that stop glitches from propagating. So we can assume that all these wires and these wires are stable. And the adversary still gets D probes. But now when we assume that when the adversary probes a wire, for example this wire, we assume that he also sees these wires. And when the adversary probes, for example this wire, he also sees these wires. So for every normal probe of the adversary, we actually give him what we call a glitch extended probe. So that is a probe existing of all the stable wires that are required to compute the normal probe. And by giving the adversary this glitch extended probe, we actually give him the power to compute the worst possible glitch function. So we can assume the worst possible glitch case is included in this model. And our very high-level view of it is very nice because it allows us to, we don't need to know what combinational logic is happening in here. It's platform independent, it doesn't depend on your place and routing, etc., etc. So that's our model. So the story of this paper actually starts with the paper that I presented last year at CHESS. So last year I presented a multiplicative masked implementation of AES. And whenever you present a masked scheme, you also have to prove that it's secure. Now this was for us very difficult, even though there are a lot of verification tools in literature. The problem was that there's two things. So first of all, we used multiplicative masking, and we also had a block that had a very heavy randomness recycling. And for those reasons, we couldn't use any of the state-of-the-art tools that are available to us in literature, because most of them actually assume Boolean masking, and also the randomness recycling is a bit tricky. So what does this mean? If you go look at that paper, you will find very long appendages with manual proofs. Now we do not like manual proofs, because firstly, they're very difficult to do, and it was also not very fun. Secondly, I don't think it's easy to read or fun to read. And thirdly, most importantly, if you do manual proofs, you have a lot of room for human error. So it's very dangerous. So we wanted to confirm we wanted to investigate the security of our scheme with automation, with tools. So one of the co-authors of this paper, had a tool at FSC 2016. So that's a tool to detect flaws in a masking scheme. And basically how it works, it's going to use a software implementation, and it's going to create simulated traces. And the simulated traces, they consist of all the intermediates in your calculation. So you collect simulated traces just like you would collect real traces from a device, and then you can do test vector leakage assessment on these traces using a t-test. If it leaks, then there has to be a flaw. The same if you want to check for higher order security, you can do it exactly as you would with real power traces. You can combine different time samples, for example, using a centered product, and then do the t-test on the longer traces. The only problem with this tool is that it was made for software, and we had to check security for hardware, so in the presence of glitches. So now we figured, let's use this tool and replace all these normal probes with glitch-extended probes. So this time our simulated traces, instead of having the exact intermediates as samples, they had the inputs of the intermediates from the previous stable stage. So you can then do the same thing. You can collect these simulated traces and do TVLA. This works perfectly for first order. But then for higher order, you need to combine samples with each other. And the problem is that you cannot just multiply different glitch-extended probes because you would lose information. So we tried to find an operation that would compress two probes into one, but as far as we know, it doesn't exist. So we decided to concatenate glitch-extended probes to verify higher order security. So, for example, for second order security, you would create a different simulated trace than for first order security. And for second order security, every sample in your trace has the concatenation of two glitch-extended probes together. And then you create those simulated traces for different secrets, and you can verify that for different secrets you get the same distribution at every time sample. So essentially what we're verifying is that the probability distribution of the probes, of the information of your adversary, for different secrets is approximately the same. It's the same as checking that the mutual information between the probes and the secret is 0. If you make simulated traces with random inputs, then you're checking the approximately 0 or approximately equal. You can also do exhaustive simulations with all the possible inputs, and in that case you can verify the exact equality. And this is essentially also what's done in the mask verif tool from Gilles Barthe, Sonia Bellent, and other people. So this is what's glitch-extended probe security. And it's not so different from probe security, because if we look at the definition from 2010, which for probe security, which said that the mutual information between D probes and the secret has to be 0, then we exactly can use the same definition, except we replace the normal probes with glitch-extended probes. So if you consider this definition being the same for glitches and no glitches, it's very simple, very short, and we're going to use now this definition and look at other security notions inside channels and kind of unify them under the same framework. When we're talking about hardware masking, we have to talk about threshold implementations because they were the first provably secure masking scheme in the presence of glitches. They depend on two key properties, which is non-uniformity and non-completeness and uniformity. For those of you who don't know non-completeness, it means that every block that is computing one output share has to be independent of at least one input share. I hope I'm pointing next week. So it's clear why this is secure against glitches, because any glitch that is happening in the block F0, for example, it cannot reveal anything about the secret because it's independent of X0. And then the other property is uniformity, which means that every possible sharing for your secret has to occur with the same probability. These two properties were the key in the proof of threshold implementations being secure against first-order DPA. And so in the paper, we do this proof with the new definition of glitch-extended probing, but I'm not going to put any proofs in the slides. The thing is that it only works for first-order security. So at Crypto 2015, it was shown that non-completeness and uniformity are not sufficient for higher-order security. This was 4 years ago, but interestingly, since then, in the last 4 years, we still see a lot of masking papers that only mention these two properties. So what can we say about these properties? So first of all, non-completeness, we know that it's not sufficient, but it is necessary, because glitch-extended probing, we can prove that it implies non-completeness. This is not really a surprise, because everyone already assumed that non-completeness was necessary, but it means you cannot use it to prove the security of your scheme, because it's not sufficient. It is very easy to verify though, so it's a very useful condition. There's a tool by Victor Arribas that very efficiently checks this condition. And if you don't satisfy it, you cannot be secure. One more thing is that non-completeness definition is quite univariate in nature, so it has not been extended yet to multivariate security. And then for uniformity, we know that it is not sufficient, but we also show in this work that's not even necessary. So if you use more than the minimum number of shares, which is what the original threshold implementations did, then you can actually have non-uniform sharings that are secure. So where does that leave uniformity if it is not necessary and not sufficient? Well, it's very helpful for constructions, because you can make, if you make sure that it's uniform in first order, then you know that it's going to, and together with non-completeness, you do know you will get first order security. But if you want to verify or prove the higher order security of your scheme, uniformity is not easier to verify than glitch extended probing security. So you might as well check for glitch extended probing security. Then another line of works in security notions for hardware security or for masking security are about non-interference and strong non-interference. These are notions that were introduced for composability, because probing secure gadgets are not composable. Another thing is that they make the verification of probing security more efficient. This was done also in the mask-proof tool from Bart and Belaid. So what do they mean? Suppose your attacker can probe a set of intermediates I and a set of output shares O, and then the set S is the set of shares that are required to simulate these probes. If that set of S is always smaller in size than the number of probes, then your gadget is non-interfering. And if it is always smaller than only the number of intermediate probes, then you have strong non-interference. And that gives you this decoupling between output and input that allows you to compose. So these notions are stronger than cheap-probing security and also more expensive. Initially, they were introduced without glitches, but last year at CHES, the robust probing model was introduced, which extended these simulation notions with glitches and other physical defects. But there was no mathematical formulation, so what we did in this work is try to unite them within our framework, and we prove that verifying these notions is the same as verifying this mathematical definition, which looks a bit complicated, so let's take an example. Suppose that you're only probing output shares and you want to verify S and I. That means that your set of shares has to be empty. So that means that you essentially want to check that the mutual information between these output shares and the input sharing is 0. So there's a subtle difference with probing security. In the case of probing security, you would check the mutual information with the secret. In this case, you check the mutual information with the entire input sharing. And this is what gives you the composability. And then, now that we have this, it's very easy to extend these notions with glitches, because all we have to do is replace the normal probes with glitch extended. So basically, the point of this presentation is that we are formulating all the security notions in this way. You have the mutual information of something with something is 0, where the first part depends on whether you are using glitches or not, and the second part depends on whether you want composability or just probing security. So what's the advantage of these mathematical formulations? So they're very simple. It doesn't matter whether you're looking at univariate or multivariate security. That's the same. You also don't require any knowledge of the variables. If you want to check non-completeness, for example, then your tool needs to know for every part of your circuit which variables belong together, which variables are shares of the same sharing. In this case, all we need to know is which wires come out of a register and where are they, which wire are they computing, etc. It's also compatible with any type of masking. We didn't assume Boolean masking or arithmetic masking or inner product masking. We also showed that non-uniformity is possible, so this might be the way to make the low entropy masking provably secure. And finally, it's also very versatile because, as we showed, you can consider glitches or no glitches, composability or not. You could also, instead of doing the information theoretical security with the exactly equal to 0, you could check more practical security by doing the approximately equal to 0 using a chi-square test, which is like TVLA in a noiseless environment. Instead of using the identity function of the probes on the left side, you could use a leakage function like Hamming weight leakage or Hamming distance. And then finally, we could start extending our models. So lately, it has become clear that there is a gap between theory and practice. So last year at CHESS, Thomas de Knude presented a work about coupling, which basically meant that the independence leakage assumption does not always hold. Another thing is that there's a lot of works that talk about the leakages introduced by a CPU in software masking. And basically what these examples show us is that our theory is incomplete because it doesn't correspond to reality. So last year at CHESS, there was a work on robust program model, which talked about a lot of other physical effects apart from glitches. So there's also memory transitions and coupling. And they extended the definitions of program security, but without a mathematical formulation. So now in this work, we provided this mathematical formulation. And the main point is that whatever new models we come up with, as long as we can define them in the sense of new probes, then we can keep using the same framework. So instead of only using glitch extended probes, you can make extended probes for memory transitions or extended probes for coupling, and we can keep using the same mathematical formulation. And more importantly, we can keep using the same tools that were made to verify these things. So to conclude, we use consolidating in our title, which is a very popular word in papers about site-channel security, but that's not the only reason we use it. According to Merriam-Webster's dictionary, it has two meanings. The first one being to join together or to unite. So what we did in this work was to unite security conditions, whether it be with or without glitches or composable or not. We try to unite them into a single framework. And then the second meaning is to make something stronger, solidify. So in this way, we try to strengthen our understanding of how to bring physical effects into our theoretical models. Thank you.